In question 1, we've got a point with coordinates 7, -2 on the curve y is f of x, and we need to state the coordinates of the image of this point when y is f of x plus 4 plus 1. Well, let's consider the two transformations which are affecting the graph here. The x plus 4 means we are deducting 4 from x, while the plus 1 means we are adding 1 to y, which means that the 7, -2, we will deduct 4 from x and add 1 to y, and this will take us to 3, -1. In part B, we've got y is f of -2x plus 7, so the -2x means we are dividing x by -2, whereas the plus 7 means we are adding 7 to y, and therefore the 7, -2 will now go to -7/2, 5. In 2a, we need to use the identity for cos of a plus minus b to prove the double angle that cos 2a is 1 minus 2 sine squared a. So let's start with the addition formula that says that cos of a plus b is cos a cos b minus sine a sine b. So starting from the left hand side, we've got cos of 2a, which we can see as cos of a plus a. So using the identity here, we can write the cos of a plus a as cos a minus sine a sine a, which is of course cos squared a minus sine squared a. Well, we're trying to arrive at the right hand side, which only involves sine. So in the place of cos squared, I'll write 1 minus sine squared a minus the other sine squared a, which leads to 1 minus 2 sine squared a, which is exactly the right hand side as required. In part B, it says hence find using calculus the exact value of the integral of 3 sine squared 2x dx from 0 to pi over 4. So I will start by using the double angle formula we have established here. The cos 2a is 1 minus 2 sine squared a, but for sine squared 2x, so we can say that cos of 4x is 1 minus 2 sine squared 2x. Now this identity will allow us to express sine squared in terms of cos of 4x. So we're looking at 2 sine squared 2x is equal to 1 minus cos of 4x, and therefore sine squared 2x is equal to 1 minus cos of 4x over 2. We will then proceed with the integral of 3 sine squared 2x from 0 to pi over 4, which I will write as the integral from 0 up to pi over 4 of 3 times 1 minus cos of 4x over 2 dx. So I can take the 3 over 2 outside. So this is going to be 3 over 2 times the integral from 0 up to pi over 4 of 1 minus cos 4x dx. And I will proceed with integrating. So the integral of 1 is simply x, and the integral of cos 4x is sine 4x, and all of it over 4. Remember, we're dividing by the derivative of the argument of sine. The derivative of 4x is 4, and the limits are 0 and pi over 4. So we're looking at 3 over 2 pi over 4 minus sine of 4 times pi over 4, and all of it over 4. That's the upper limit substituted, and if I substitute the lower limit, I get 0 minus 0 because sine of 0 is 0, and this simplified will lead to an answer of 3 pi over 8. In question 3, we've got the formula for the number of guinea pigs capital G T months after being introduced. A is a positive constant, and similarly another formula for the number of rabbits capital R. And then we know that there were twice as many guinea pigs as rabbits introduced onto the island, and we need to work out the value of A. So when they were introduced, this means that T is 0. So when T is equal to 0, we will start by finding G and then R. So G is equal to A plus 60 times e to the power of 0, which is of course A plus 60, whereas R is 100 plus 80 times e to the 0, which gives an answer of 180. Well, we are told that the number of guinea pigs is twice the number of rabbits, so G is 2R. So A plus 60 is equal to 2 times 180, leading to A plus 60 being equal to 360, and therefore A is equal to 300. We are then told that when T is capital T, the number of rabbits is equal to the number of guinea pigs, and we need to find the value of capital T, giving our answer to 1 dp. So let's start by stating what we have been given. So at T is equal to capital T, G is equal to R. Well, G is the 300 we just found for A, plus 60 e to the minus 0.05 capital T, which is equal to 100, plus 80 e to the 0.05 capital T. I will be collecting everything on the right hand side, leading to 0 is 80 e to the 0.05 capital T, minus 200 minus 60 e to the minus 0.05 capital T. I will then divide everything by 20, leading to 0 is 4 e to the 0.05 capital T, minus 10 minus 3 over the e to the 0.05 capital T. So the e to the negative 0.05 T, I wrote it as e to the 0.05 capital T in the denominator. And then I will introduce another variable. I will call it W, and I will say let W be e to the 0.05 capital T, which means we're looking at 0 is 4W minus 10 minus 3 over W. The obvious next step is to multiply throughout by W to obtain a quadratic in W. So this is 4W squared minus 10W minus 3. I will use the quadratic formula to extract the two possible values for W. So it's minus negative 10 plus minus the negative 10 squared minus 4 times negative 3. And I'll take the square root here and all of it over 2 times 4. So the two solutions we get are W is 5 plus root of 37 and all of it over 4. Or alternatively, that W is 5 minus root of 37 and all of it over 4. Now for this second solution, this means that W is minus 0.27069 ... and remember that W is e to the 0.05 capital T. So we can see that there are no solutions on this part, because if I raise e to any power, I cannot get a negative result. It's always going to be positive. So I say reject here. It's not valid. And the only solution will come out of the first solution of W being 5 plus root 37 over 4. If I put these numbers on the calculator, I get that W is 2.77069 ... So e to the 0.05 capital T is 2.77, and then I will proceed by taking ln to get 0.05 capital T is ln of 2.77069. Now I will divide both sides by 0.05 to leave capital T on its own, and if I put this on the calculator, it gives an answer for capital T, which is 20.4, correct to 1 decimal place. In question 4, we need to show all stages of the working, and solutions relying entirely on calculator technology are not acceptable. We need to solve for theta between 0 and 2 pi, so we are in radian mode. The given trigonometric equation giving each answer to two significant figures. Well, we've got 3 sine 2 theta plus 5 cos 2 theta on the left hand side, and we can proceed by combining them together into a single sine using the R formula. So we've got 3 sine 2 theta plus 5 cos 2 theta is equal to R sine of 2 theta plus alpha, and the objective is to find R and alpha. Well, on the right hand side, I will be expanding this using the addition formula for sine A plus B, leading to R sine of 2 theta cos alpha plus R cos 2 theta sine alpha. And then I will be equating the sine 2 theta terms and the cos 2 theta terms. So I've got 3 sine 2 theta is equal to R sine 2 theta cos alpha, and then 5 cos 2 theta is equal to R cos 2 theta sine alpha. This means that we've got 3 is equal to R cos alpha and 5 is equal to R sine alpha, leading to 3 over R is equal to cos alpha and 5 over R is equal to sine alpha. I can then draw a right angle triangle as shown here. We've got cos is 3 over r, so it's adjacent over hypotenuse, and sine is 5 over r, so it's opposite over hypotenuse. I can use Pythagoras to say that r is 3 squared plus 5 squared square root, which gives an answer of root 34, whereas tan alpha is equal to 5 over 3, and I can find alpha by doing shift tan of 5 over 3. This gives an answer of 1.03 ... So if I get my calculator, I'm gonna do shift tan of 5 over 3. I will press the equal sign and then I will store it on A. So now I've stored the value of alpha, the exact value, on my A key here. So let me make a note. This is stored on A, which means I can now proceed in saying that 3 sine 2 theta plus 5 cos 2 theta is equal to root 34 sine of 2 theta plus the A we stored on the calculator. Now we know that 3 sine 2 theta plus 5 cos 2 theta is equal to 4. So we've got root 34 sine of 2 theta plus A is equal to 4. And therefore sine of 2 theta plus A is equal to 4 over root 34. I will proceed by finding the principal value. So I'll be doing PV is shift sine of 4 over root 34. So once more, I'm gonna go on my calculator. I will do shift sine of 4 over root of 34. I will press the equal sign. This number will now be stored on B, so I will store this on B. So it's 0.7559. Let me write this down, 0.7559 ... which I have stored on B. And we know that when we are solving trigonometric equations involving sine, it's the PV plus 2 pi k or pi minus the PV plus 2 pi k. So we've got 2 theta plus A is equal to the PV of B plus 2 pi k, or 2 theta plus A is equal to pi minus the PV plus 2 pi k. I will be solving for theta, so 2 theta is equal to B minus A plus 2 pi k, which means that theta is a half of B minus A plus 2 pi k, or 2 theta is pi minus B minus A plus 2 pi k, which means that theta is a half of pi minus B minus A plus 2 pi k. And I can actually automate the whole process on the calculator. So I press menu, it's option 9. My f of x is a half of the B minus the A plus the 2 pi x, and I close brackets, and my g of x is a half, and I've got brackets here, it's pi minus the B minus the A plus 2 pi x. I close the brackets. I will start at -2. I will go up to 5, saying we're looking for solutions between 0 and 2 pi. So all of these are solutions here. I will only pick the ones that are positive and less than 6.28, which is the value of 2 pi. I see I've got 0.6776. Remember, we need to report answers to 2SF, so 0.68. The next solution is here, it's 3.0, and if I move to the right, it's 3.8, and finally if I go down and to the left, it's 6.1. So we've got a total of 4 solutions. In question 5, we've got the function f of x defined here for x in the reals and x being greater than -3, and we need to show that f of x can be written in the form of a over bx plus c, with a, b, and c being constants to be found. So starting with the expression for f of x we've been given, the first sensible thing to do is try to factorize the second denominator. So this is 7 over x plus 3 minus 5x plus 22 over x plus 3 x plus 4. So I can see that I can express everything over a common denominator of x plus 3 x plus 4. So let me write this down. And then the 7 needs to be multiplied by x plus 4 minus brackets the 5x plus 22. I will expand the numerator to get 7x plus 28 minus 5x minus 22, and all of it over x plus 3, x plus 4, where the numerator simplifies to 2x plus 6, and this is over x plus 3, x plus 4. I will then factorize the numerator to give me 2 brackets x plus 3 over x plus 3, x plus 4, and we obviously see the x plus 3 cancelling out, leaving us with 2 over x plus 4, and therefore we conclude that the constant a is 2, b is 1, and c is 4. In part B, you need to find the inverse of f, and we will be using the simplified answer we obtained in part A. I will start by writing y is the simplified expression, so 2 over x plus 4. When finding the inverse, the first thing to do is interchange x and y, so x is 2 over y plus 4. And I will now try to make y the subject, so x brackets y plus 4 is equal to 2, so xy plus 4x is 2, which means that xy is 2 minus 4x, and therefore y is 2 minus 4x over x, and therefore we conclude that f inverse of x is 2 minus 4x over x. This will give me 2 out of the 3 marks. The third mark is for me to identify the domain of the inverse, and the domain of the inverse is the range of the original function. So I will do this by sketching f of x. Now recall that f of x is 2 over x plus 4 for x being greater than negative 3. I will start by finding the equations of the asymptotes. We've got a horizontal and a vertical asymptote because this is a reciprocal curve. Now we know that we've got an issue when x plus 4 is 0, and we've got division by 0, f of x is undefined. So the equation of the vertical asymptote is x is negative 4, and for the horizontal asymptote, I consider what happens to y as x goes to infinity. So as x goes to infinity, essentially the denominator explodes, so we've got 2 over infinity, so we can see that y tends to 0, and therefore the equation of the horizontal asymptote is y is equal to 0. I can also further proceed into finding the value of y when x is 0. This is the cut on the y-axis, so if I put x is 0, I get 2 over 4, which simplifies to a half. And another crucial point is the end point here of minus 3. So when x is negative 3, if I substitute, I get that y is equal to 2. So starting with my axis, we've got the vertical asymptote at x is negative 4. The graph looks something like this, cutting the y-axis at a half. It's restricted here at negative 3, at which point y is 2, and we're only looking on the right-hand side of this. So we can see that the output of f of x lies within this corridor between 0 and 2, and therefore the range of f of x is 0 less than y less than 2. Now the range of f of x is the domain of the inverse, so coming back here to f inverse of x, the domain will be x belongs to the reals, and 0 is less than x, which is less than 2. In part C, we need to solve f of x is 2 over 5. So one way to proceed will be to find the composite function f of x. An alternative way, which I prefer, is to start exactly with what we are given and then just do f inverse of both sides. So f inverse of f of x is f inverse of 2 over 5. Now the reason I chose this approach is that the f inverse with f will cancel out, leading to f of x is f inverse of 2 over 5. So I will be substituting 2 over 5 into the expression we just obtained here in part B. So this means we're looking at 2 minus 4 times 2 over 5, and all of it divided by 2 over 5. So we've got that f of x is equal to 1, and then I will repeat the process once more. I'll do f inverse of both sides. So f inverse of f of x is f inverse of 1. Once more, the f inverse of f will cancel out, leaving me with x is 2 minus 4 times 1 over 1, therefore concluding that x is equal to negative 2. In question 6, we've got a sketch of the curve with the equation y is the modulus of sine x plus 1 between 0 and 2 pi. We've got the point P with coordinates A, B shown here lying on the curve having a gradient of negative a half, and we need to determine the exact value of A and the exact value of B. Well, let's start by considering exactly how the graph was derived. Starting with sine of x, it's like this. Now the modulus of sine x is making everything positive, so it's like this, and then adding 1 will take me here. So this point is the pi and this is the 2 pi, so let me write this down, and then we know that this hump here is the sine of x plus 1, and the second hump here is minus sine of x plus 1 because of the reflection along the x-axis. So this means that if I'm trying to determine the coordinates of P, knowing that it has a gradient of negative a half, I need to start by differentiating this expression here. So we know that if y is minus sine x plus 1, then dy dx is equal to minus cos x, which I will set equal to minus a half, and therefore I need to solve cos x is a half. Now the PV here is shift cos of a half, which gives me an answer of pi over 3, and therefore x is plus minus the PV of pi over 3 plus 2 pi k. Well, if you think about it, we are trying to find the solution which lies between pi and 2 pi. We can certainly see that the first solution that this equation will yield is x is pi over 3, which is not good, but the second solution is 5 pi over 3, which is actually the solution we are after, and therefore we conclude that the x coordinate is 5 pi over 3. And for the y coordinate B, I will evaluate this when x is 5 pi over 3, so it's minus sine of 5 pi over 3 plus 1, which leads to an answer of B being root of 3 over 2 plus 1. We then have that the straight line with positive gradient passes through the point P, and we know that this straight line is intersecting at exactly 3 distinct points, and we need to find the range in values of the gradient of the line. So let me start by adding the coordinates of P here, and if you think about it, if I draw a line passing through this point here, we've got exactly 2 cuts. If I draw a line passing through the y-intercept, we've got 1, 2, 3, 4 cuts. So anything in between will give me 3 distinct cuts. So the first important line is the one passing through the y-intercept, which is 0, 1. And the second crucial line is the one passing through this point here, the pi over 1. And if we go into Desmos, we've got the graph shown here. We've got the straight line going through P. So if we play around with the gradient, we can see that this is exactly one of the crucial points. We've got 2 points of intersection. Then it's 3 points of intersections up to the moment we pass through the y-intercept, at which point we've got 4 distinct points of intersection. So essentially, we need to find the 2 gradients that match the 2 straight lines, and anything in between will be yielding 3 distinct cuts. So for the line passing through 0, 1, we've got that the gradient is rise over run, so it's root 3 over 2 plus 1 minus 1 over the 5 pi over 3 minus 0. This gives an answer of root 3 over 2 over 5 pi over 3, which simplifies to 3 root 3 over 10 pi. Whereas for the straight line passing through pi 1, I will repeat the process. We've got m is root 3 over 2 plus 1 minus 1 over the 5 pi over 3 minus pi, leading to root 3 over 2 over 2 pi over 3, which gives an answer of 3 root 3 over 4 pi. So anything in between these two will be giving me 3 distinct cuts. Therefore, we conclude that 3 root 3 over 10 pi should be less than m, which should be less than 3 root 3 over 4 pi. In question 7, we've got y is e to the 2 root 3x cos 2x, and in part A we need to find dy dx. So we will be applying the product rule here. If we differentiate e to the 2 root 3x, we get 2 root 3 e to the 2 root 3x, and we keep the cos of 2x, plus we keep the e to the 2 root 3x, and we differentiate cos of 2x, which will give me minus 2 sine 2x. Notice that I have not been told to simplify this. It's just the expression for dy dx, so this will give me the 2 marks. And then in part B, we need to use algebra, and showing the working, we need to find the exact coordinates of the stationary points on the curve. Well, we know that stationary points means that dy dx is 0. So we've got 2 root 3 e to the 2 root 3x cos of 2x plus e to the 2 root 3x times minus 2 sine 2x is equal to 0. I will start by dividing throughout by e to the 2 root 3x. I will also simplify the 2, and this leaves me with root 3 cos of 2x is equal to sine of 2x. I will then proceed by dividing both sides by cos of 2x. So what we will be looking at is root 3 is equal to tan of 2x. So I need to solve this trigonometric equation here. So the PV is going to be shift tan of root 3, which gives an answer of pi over 3. And for tan, we know that it's going to be 2x is equal to the PV of pi over 3 plus pi k. I will divide by 2 to get x is pi over 6 plus pi k over 2. And therefore, we can now proceed in generating all solutions. Remember that x is between 0 and pi. So the first solution is that x is equal to pi over 6, in which case y is equal to e to the 2 root 3 pi over 6 times the cosine of 2 pi over 6. Remember, we're trying to find the exact coordinates here. The cosine of 2 pi over 6 is simply a half. So we've got e to the root 3 pi over 3 and all of it divided over 2. And the second solution will be at x is 2 pi over 3. This is obtained by setting k here to be 1. And therefore we have that y is e to the 2 root 3, 2 pi over 3 times cosine of 2 times the 2 pi over 3, which gives an answer of minus e to the minus 4 root 3 pi over 3, all of it divided by 2. And therefore we conclude that the two stationary points have coordinates pi over 6, comma e to the root 3 pi over 3, and all of it over 2. That's the first stationary point. And the second stationary point, it's 2 pi over 3, comma minus e to the minus 4 root 3 pi over 3, and all of it divided by 2. Question 8, we've got the population P in thousands of people modeled through A, B to the negative T. T is the number of years since the beginning of the monitoring, and we need to show that this equation can be expressed in this form. So starting with what we are given, the obvious thing is to take everything to log base 10. So we're looking at log of P base 10 is equal to log of AB to the negative T base 10. Well, on the right hand side, we've got log of A base 10 plus log of B to the negative T base 10. So on the left hand side is still log P base 10. So log of P base 10 is equal to log of A base 10, and the negative T can come down, minus T log of B base 10 as required. We are then given a line of best fit, and we are told that we are passing through 0, 1.6 and 10, 1.4, and we need to use this information to obtain A and B to 4 significant figures. Well, I will start by finding the gradient of this line. So I'll be doing rise over run, leading to m being 1.4 minus 1.6 over 10 minus 0, which means we're looking at the gradient of negative 0.6. 0.02, whereas the y-intercept c is 1.6. So since the x-axis is t and the y-axis is log of p base 10, we can simply say that the straight line is of the form log of p base 10 is equal to 1.6 minus 0.02t. We also have from part A that log of p is log of a minus t log b base 10, so we can compare. The 1.6 is the constant, which should be equal to log a base 10, and the 0.02 should be the log of b base 10. So log of a base 10 is equal to 1.6, which means that a is 10 to the 1.6, which correct to 4 significant figures is 39.81, whereas log of b base 10 is equal to 0.02. So b is 10 to the 0.02, which gives an answer of 1.047. And in part C, we need to find the rate at which the population is changing 8 years after the monitoring began. Let's start by writing down the equation for P. It's 39.81 times 1.047 to the negative t. And then we will find dp dt, the rate of change of the population. So 39.81 is a constant, but for the derivative of 1.047 to the negative t, well, the derivative of negative t is simply negative 1, and 1.047 to the negative t times ln of 1.047. So we need to evaluate this derivative at t is equal to 8. So I will substitute t with 8. So we've got minus 39.81, 1.047 to the negative 8 times ln of 1.047. If we plug this on the calculator, we get an answer of minus 1.268. And bearing in mind that p is measured in thousands, we are looking at a decrease of 1,270 per year. In question 9, we've got x here in terms of y, and we need to show that the equation of the curve can be written in this form. So starting with the expression for x, an idea is to multiply top and bottom by cos y plus sine y. So we are multiplying by 1 in an intelligent way. So if I expand the numerator, I get that x is sine y cos y plus sine squared y minus cos squared y minus sine y cos y, whereas in the denominator, if we do the expansions, we'll get cos squared y plus 2 sine y cos y plus sine squared y. Well, we can see that in the numerator, the sine y cos y will cancel out, and we can write this as x is minus brackets cos squared y minus sine squared y, whereas in the denominator, the cos squared y plus sine squared y is simply 1, and the 2 sine y cos y is the double angle for sine, so plus sine 2y, and then x is minus cos of 2y over 1 plus sine 2y, using the fact that cos squared y minus sine squared y is cos of 2y. In part B, we need to show that dx dy is 2 over 1 plus sine 2y. So starting with the expression we arrived at in part A, we will apply the quotient rule of differentiation. So dx dy, the derivative of cos is negative sine, and I also need to multiply by the derivative of 2y, which is 2. So this is 2 sine 2y, and I keep the denominator of 1 plus sine 2y, minus I keep the numerator of minus cos 2y, and I differentiate the denominator, where the denominator will give me a derivative of 2 cos 2y. So let me write this down, and it's everything over the original denominator squared, so 1 plus sine 2y squared. So if we expand the numerator, we get 2 sine 2y plus 2 sine squared 2y plus 2 cos squared 2y, and all of it over 1 plus sine 2y squared. So in the numerator, I can group together the sine squared plus cos squared terms, so 2 brackets sine squared 2y plus cos squared 2y, close brackets, over the denominator of 1 plus sine 2y all squared. Now obviously the sine squared plus cos squared is 1, so we've got 2 sine of 2y plus 2 over 1 plus sine 2y squared. So what I can do is factor out the 2 from the numerator to get 2 brackets sine of 2y plus 1, close brackets, over 1 plus sine of 2y squared. So we see now that the 1 plus sine 2y will cancel out, leaving me with 2 over 1 plus sine of 2y as required. And finally, in part C, we've got a point P, at which point the y dx is a quarter and y is negative, and we need to determine the exact coordinates of P. So knowing that the y dx is equal to a quarter, we can safely conclude that dx dy is equal to 4. So I just flip this. So we've got the expression we obtained before for dx dy of 2 over 1 plus sine 2y being equal to 4. So I need to solve this trigonometric equation. I will start by cross multiplying. Leading to 2 is 4 plus 4 sine 2y. So negative 2 is 4 sine 2y. So minus a half is sine of 2y. I will proceed in finding the principal value. So the PV will be shift sine of minus a half, which is minus pi over 6. Leading to 2y is the PV of minus pi over 6 plus 2 pi k, or 2y is pi minus the PV plus 2 pi k. I will divide by 2. This will lead on the left hand side to y is minus pi over 12 plus pi k, and on the right hand side I've got y is 7 pi over 12 plus pi k. Remember, we have been given that the values of y vary between minus pi over 4 and 3 pi over 4, and the particular value we're trying to find is a negative 1. So we can see that the only solution which is yielding out of these equations is y is minus pi over 12. So this is the y coordinate of the point. And I just need to find the corresponding x coordinate. So x is going to be minus cos of minus 2 pi over 12 over the 1 plus sine of minus 2 pi over 12. So I'm substituting in the expression for x. This gives me a result of minus root 3. And therefore we conclude that the coordinates of P are minus root 3, comma minus pi over 12. In question 10, we've got a sketch of the curve with this equation here. We are crossing the x-axis at point P with coordinates alpha 0, and we need to show in part A that alpha satisfies the given equation. So we know that at point P, we've got that x is alpha and y is 0, which means I can substitute into the given equation for the curve, leading to 0 is equal to e to the 2 alpha minus 3 minus 4 over 3 alpha. So we've got that 4 over 3 alpha is e to the 2 alpha minus 3. Well, I will take a ln of both sides, so a ln of 4 over 3 alpha is equal to 2 alpha minus 3, which means that a ln of 4 over 3 alpha plus 3 is equal to 2 alpha. I will then divide both sides by 2, leading to a half. A ln of 4 over 3 alpha plus 3 is equal to alpha as required. In part B, we are given this iteration formula. We are starting at x naught is 2, and we need to find x1 and x5, giving each answer to 4 decimal places. So we are starting at 2. So I'm going to go on my calculator. I press 2 and the equal sign. So I've stored 2 on my answer key. And then I will do a half of a ln of 4 over 3 uns, and I will close these brackets, plus 3 and close the bracket. So every time I press the equal sign, it's a new iteration. So I press it once and I get 1.2973. So x1 is 1.2973 to 4 decimal places. This is x2, x3, x4, and x5. So x5 turns out to be 1.4537. In part C, we need to use a suitable interval and a suitable function that should be stated to show that the solution alpha is 1.456 correct to 3 decimal places. So I will start by defining f of x to be e to the 2x minus 3 minus 4 over 3x. This is simply the y, the equation of the curve. We've got alpha is 1.456, which I will split into 1.4565 and 1.4555. So I'm looking for a change of sign over this interval here. So whatever lies between these two will round to 1.456 correct to 3 decimal places. So I need to evaluate f of 1.4565 first. So I'm going my calculator. I press 1.4565 and I store it on my answer key. And then I will do e to the 2 uns minus 3 minus 4 over 3 uns. I press the equal sign and I get an answer of 0.00124, and I need to do the same for f of 1.4555. So on my calculator I press 1.4555, I press the equal sign, I store it on my answer key, and I press the cursor up to obtain the previous expression. I press the equal sign, and this is negative 0.00122. So this is the change of sign. The first value was positive, the second value was negative. And this means we can proceed into writing a conclusion. We've got a change of sign and f of x is continuous. Hence, we've got a root within this interval here, i.e. my solution alpha is 1.456 to 3 dp's. Be careful here, you need to mention both the change of sign and the continuity of f of x to qualify for the final mark. In part D, we're asked to use integration to find in its simplest form the shaded area here, which is the area bounded by the curve, the x-axis, and the lines x is negative 4 and x is negative 2. So in other words, we need to evaluate this integral here. Well, the integral of e to the 2x minus 3 is simply e to the 2x minus 3 over 2, whereas the integral of 4 over 3x is simply 4 over 3 ln of the modulus of x, and the limits are negative 4 and negative 2. Let me substitute the upper limit. So we've got e to the 2 times negative 2 minus 3 over 2 minus 4 over 3 ln of the absolute value of negative 2 minus the lower limit, so e to the 2 times negative 4 minus 3 over 2 minus 4 over 3, and we've got ln of the absolute value of negative 4. This leads to e to the minus 7 over 2 minus 4 over 3 ln 2 minus e to the minus 11 over 2 plus 4 over 3, and we've got ln of 4. So what I can do is play a bit around with ln 4 to combine it with ln 2 here. So we've got e to the minus 7 over 2 minus 4 over 3 ln 2 minus e to the minus 11 over 2 plus 4 over 3, and 4 is simply 2 squared, so that the 2 can come down, leading to e to the minus 7 over 2 minus 4 over 3 ln 2 minus e to the minus 11 over 2 plus 8 over 3 ln 2. So the 2 came down, multiplying the 4 over 3 by 2, leading to 8 over 3. So we conclude that the final answer is e to the minus 7 over 2 plus 4 over 3 ln 2 minus e to the minus 11 over 2.